What's going on, folks? Hey, I actually wanted to teach you folks a little bit about how to find a derivative and where it comes from, and then we'll go into a little bit about how to find the first rule of taking the power rule of derivatives. And my goal here is, with me today I have my son, and my son, his name is Ben. Say hi, Ben.
Hi.
And what he's in algebra 2. And what my goal is to try to see if I can explain this concept so well that he can understand. So I'm going to encourage him to ask me questions, to pause, and to say, hey, wait a second, that doesn't make sense. Because if I can explain it to someone who's in algebra 2, that means I know that this is something that everyone can follow. Is that about right?
Yeah.
You cool with that, Ben?
Uh-huh.
Okay, so finding the derivative. Actually, here, let me just, this one, D. Sorry, the computer froze a little bit. Okay. All right, finding the derivative. All right, so what we're going to have to do is what we're looking for is we want to find the slope. Say that we have a graph, and the graph looks something like this. Okay? And we want to find the slope of a tangent point. And let me explain to you what a tangent point is. If you have a single point right here, and you have like a ruler that balances on this thing, and it only touches at this one point, that is what we call a tangent point. Does that make sense?
Mm-hmm.
Okay. So we want to find the slope of that tangent point on this graph. And if I have a different tangent point, like let's say this point right here, then the tangent line would look something like this. Are we go with that?
Mm-hmm.
So what we're trying to do is we're trying to find the slope of some point on this graph. Now, here's the really funky part is if I were to ask you, okay, draw a line that I'm thinking of that goes through this single point right here, what would you say? Here, you draw it. Wrong. That's not the point I was thinking of. I was thinking of this point, or this line right here.
So, does it really matter, or does it?
Yeah, it totally does matter. But the problem is you asked me to draw, or I asked you to draw a line that was going through a single point. And there's many, many lines that can be drawn that goes through that single point.
Mm-hmm.
You know what I mean? It doesn't even make sense if I ask you, draw the one that I'm thinking of that goes through that one point. Because unless you are incredibly lucky, you probably won't draw the line that I'm thinking of. But what if I said, okay, draw the line that I'm thinking of that goes through these 2 points? Then what would you say?
Then I would say.
Absolutely. That's exactly, how did you know that's exactly the line I was thinking of as well? That's a miracle, right?
Yeah.
No, it's not really, because if you have 2 points, then you define the line. If you have 1 point, it's an undefined line. It doesn't really make sense to find the slope of a line that going through 1 point, because it could be any slope. Do you see what our problem is here? What our problem is I just told you that the tangent, the definition of tangent, means we're trying to find the slope of the line that goes through this single point and only touches at that 1 point. But then what you're going to say is, but wait a second. In order to find that slope, and if you're talking about a line in the first place, don't you need 2 points?
Yeah.
In fact, unless I have 2 points, it's not really defined as a line. Does that make sense?
Mm-hmm.
Okay, so I'll show you the trick that we do. Imagine this black thing is like a wire hanger that I've bent to look like the function right here. Okay,
Yeah.
and I take 2 beads and I put them on this wire hanger. Okay, And I use a laser or something like that too, so that way you can see the line that connects these two beads. Okay?
Yeah.
Can you find the slope of that blue line?
Yes.
Absolutely. And then here's, I'm going to show you what I'm going to do first, and then we'll actually do it. Then what it says, okay, well, you can find the slope of that blue line. Correct. Okay, good. What if I move that? What if I see this first bead is locked into place? Well, what if I move this second bead closer to where the first bead is? Okay, well, the new slope is going to look like this. Right?
Yeah.
Okay. And would you say that's more similar or less similar to the red slope?
It's more similar to the red slope.
Okay. What if I move the second bead even closer? Like, let's say right here. Then the blue line's going to look more like that.
Yeah.
Is that more or less similar?
More similar.
Even more similar. Okay. What if I move that blue line so that way it's almost pretty much on top of the first blue bead?
Then it will probably be the exact same line as the red line.
Yeah, exactly. But the blue line is defined by 2 points, which is what we want. Even though those 2 points might be very, 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 very close to each other, it's still 2 separate points. And the key is, once we have that, then that blue line will almost look, effectively, it will look identical to the red line. And now, voila, we've figured out what the red line is. That's how we're going to do that. So first, what I need to do is kind of do some preliminary math, like some remember this kind of math. All right. What is slope? Do you remember what slope is?
I think it was like y equals.
You're trying to spout off an equation, like y equals blah 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 blah. Well, here, all it is it's rise.
Oh yeah, rise.
Over run. We cool? And what that is when I taught you defining a slope, I told you, okay, well, you have a x2 and a y2 over here, and a x1 and a y1. And so the rise is equal to the change in height, so that would be y2 minus, do you remember?
Y2?
No.
Oh, x2?
Nope. Y2 minus y1, it's a change in height, right? Divided by x2 minus x1. Cool?
Yeah.
And that is not calculus stuff. That's not even trigonometry stuff. That's algebra 2 stuff.
Maybe algebra 1.
It might even be algebra 1. I totally agree with you. Cool? Well, if it was algebra 1, why didn't you remember it?
It's been a long time.
Okay. All right. Anyway. So, that's all we need. This calculus is actually based on slope equals rise over run. And you're going to be like, you're kidding me, right? And I say, no, actually I'm not. Let me show you. So, we started off with saying, okay, imagine there was 2 separate beads. And this axis right here, the horizontal axis, let's call X. And this vertical axis, let's call, not Y, I'm going to call it f of X. We cool? Now I'm going to call this specific point X is equal to A. Are we cool with that?
Yes.
And I'm going to call this second point X is equal to, well, let's just call it X. All right? Now, the corresponding Y value to this A position is actually f of A. Let me do that better. F of A. Are we cool?
Yeah.
You sure? Okay. And the corresponding X value to this thing is f of X. Good? So therefore the slope is equal to y2, which is what?
That would be x fx.
F of x, good. Minus y1, which is f of a, good. All divided by x minus a. Exactly. Very good. Now, what we're going to do is, if we want to find the slope at that one particular point, so we call this, the way we're going to denote this is this is f prime of a, also known as d dx of f of x. If I evaluate at a, that's how you could write it. This is saying I'm taking the derivative of this thing with respect to x, and that's equal to this right here. But not just this. This is the slope of the blue line, right?
Yeah.
What I want is the slope of the red line. So what I'm going to do is I'm going to say I'm going to take, and this is where the calculus comes in, okay? I'm going to take the limit as x goes to a. So what that's saying is, let x get closer and closer and closer to a. Then my blue line will become what I'm looking for. And this is the calculus part. It's where we start moving things. And then my original equation is f of x minus f of a, all divided by x minus a. That is the equation for a derivative. That's actually not that bad. I mean, you would think that it's really complicated, and we spend half of calculus studying derivatives, and yet that's all it is. All we're doing is finding the slope. And we're taking the limit as x goes to a, and that can be tough. But it really isn't that bad. Now, you might see a different definition of a derivative, okay? So this is one of them. This is an equation that we should write down. Let me show you a different definition because it might look a little bit different. And all I'm going to do is I'm going to argue that it's actually really the same thing. It just looks a little bit different. Let me redraw my graph. Cool? This is x and this is f of x. And what I'm going to do is I'm going to define the first point as a. Nothing new there. Cool?
Yeah.
And instead of defining the second point as x, oh, okay, I'm sorry. And if that's a, then this is what? F of a? All right. Instead of defining the second point as x, what I'm going to define is the distance between this point a and this point, the second point, whatever it is. I'm going to define that as h. Ask me why h?
Height?
No. I have no idea why h. It just is. It was another letter in the alphabet and we were happy about it. Cool? I'm sure that there's some grand reason and I have no idea. Or maybe someone just made it up just because it's h. Alright. That would mean this point right here is actually whatever a is plus h. Are we cool? And the corresponding y value for that is f of what?
F of a plus h.
Good. A plus h. That's it. All right, so finding the derivative of this is, okay, what is the y2 in this case?
The y2 would be... Oh, the y2 would be f of a?
F of a plus h, right? It's the higher one, minus
F of a.
Good.
And then
all over
a plus h and
a plus h
minus a.
minus a. Oh, by the way, a plus h minus a is what?
Just h.
Good, good, good. So this is f of a plus h minus f of a, all divided by h. And I'm taking the limit as what? Stop playing with that and look, what are we doing? I'm taking the limit as something gets closer to something else.
So this is the limit? Or
No. What I'm doing is, look at the second bead. I'm moving the second bead along this function, and I'm making it get closer and closer to that first bead, right?
Mm-hmm.
So h, does it get bigger or smaller?
It gets smaller?
Right, because h is defined as what again?
It's defined as just h.
No, it's defined as the distance
the
between
distance
this point, the first bead, and the second bead. And if I move the second bead closer to the first bead, then h is getting smaller. And if I basically move the second bead on top of the first bead, what does h go to?
Like a, pretty much.
A. Oh, no, no. You're thinking. You're still thinking back in terms of this, where x goes to a. No, I'm talking about this distance between the second bead and the first bead gets so small that it effectively becomes.
Nothing really.
Okay, rhymes with hero, starts with a Z.
Zero.
Zero. Oh, wow! How'd you guess it? All right, the limit as h goes to 0. Now, you will see a derivative defined like this. And I will show you in my book so that way you know that I'm not making this stuff up. Okay, derivative rules. Give me a second. I'm just looking through my book. There we go. Look at that.
Oh, cool.
I think the book did it a little bit differently. They go like this. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. That's how they wrote it, and all they did that's different from how I wrote it is instead of an a, they put an x. But it's the same thing. And actually, this thing that I have boxed up down here is the same as what I have boxed up here. It might look a little bit different. It's not different. It's the same basic equation. I'm just defining terms differently. In this case, I defined this as a and this is x. Whereas in the second case, I defined it more as this is a, and then the second most important variable is this distance between the second bead and the first bead.
Yeah, but where did the d over...
Oh, the ddx? That is the way that we write the derivative. It's it looks like this, ddx, because we're taking the derivative with respect to the x axis. If this were instead the theta axis, we would call this dd theta. Does that make sense? But instead it's the x-axis, and so we're going to stick with it being ddx. That's where that comes from. Don't get that confused with d divided by dx. That's totally wrong. And that's an excellent question. In fact, that's actually why I have you here, because you're looking at this and wondering, wait, what are these? Why is it a division? D divided by dx? That doesn't make any sense. No. It's really just kind of a notation that we use to say I'm taking the derivative of f of x with respect to the variable x. Cool?
Yeah.
Another very shorthand, lazy way to write it, and I actually don't mind the lazy way. I like it, especially at the beginner level calculus, is just to put a little single quotation mark. What do they call that? A semicolon? I don't know. I've never been good at English. No, semicolon looks like this. No. This is like just a comma. We put a little comma right there. And that says I'm taking the derivative of f of x. We cool? Okay. The next thing I'm going to show you is the power rule. And I'm going to record that in a different video because I don't want these things to get too cluttered up.